We're going to take it live, and I'm going to start going into the stuff real quick. And so I'll let you know when you're up. Go. You're good, Dr. Barr.
Okay. Afternoon, everybody. Welcome to the 71st episode of the How Do You Know program. I'm Dr. Daniel Barth, author of Star Mentor, Astronomy for Educators, and other titles. And we're here with you again with another weekly exploration of astronomy and space science. So this week, we're going to touch on exoplanets. We talked about planets last week. With minor planets like Quaoar having rings where they're not supposed to. And we touched on the idea that the current definition of planet only applies to things orbiting our sun, which is kind of silly, but there you go. So I thought I would look into some information on exoplanets. And as I crawled in and was looking at some more new stuff, it dawned on me we haven't had a really good show on exoplanets, what they are, and how do we find them. And when I mentioned this idea to a friend, the friend, almost like a Hollywood straight man, said, but how do they know there's really exoplanets out there? And so I thought, I'm sure there's lots of other people with the same question. So we're going to take a look at that this week. So when we talk about exoplanets, what are they? Exoplanets are planets which orbit other stars than our sun.
Dr. Barr.
Now, this is yes.
Don't forget about your book.
Oh, quite right. We mentioned that, but we'll mention it again. You see the nice image there. Paul has put it up for us. Star Mentor. I've compressed 50 years of teaching astronomy to beginners into one easy-to-read book that's fun for novice and intermediate astronomer alike. Star Mentor gives you more than 50 projects that you can do at home with a small telescope or binocular. I know sometimes people say, well, I only have a telescope and it's only this big. And they say, well, that's all right. Galileo did amazing things with a telescope with a lens no bigger than a quarter. And so when we talk small telescopes here, Paul, we're talking about a Dobsonian telescope of 6 inches or less, a refractor of 90 millimeters or less, your common variety 60 millimeter department store refractor would be fine for much of the stuff we do here. There are activities with learning the night sky, constellations, finding out how the stars move, tracking planets. There's some things on galaxies which would require a little bit bigger telescopes, but it's not the kind of book where you go from start to finish. It's designed to be a smorgasbord, a delightful palette of wonderful things that you can do. If you've ever seen someone with a new telescope who asked, but what do I do next? I've looked at the moon. I've seen the moons of Jupiter and the rings around Saturn. What do I do next? Star Mentor is your answer to that question. I urge you to check out Amazon or a bookstore and purchase your copy. And if you do purchase a copy, please leave us a review on Amazon. We appreciate those reviews, every single one of them. So there's our email address, astronomyforeducators@gmail.com. If there's a science or astronomy topic you would like us to seriously consider, then I would be happy to have your email. And if you would just love sometime to be a guest on our program, then please send me an email. We'd love to have guests, especially if you have a particular topic or something you're interested in. I'd love to have a discussion with you about your special topic, because I'm sure if you're interested in it, there would be lots of other viewers who are interested too. So today, we're kind of jumping off the deep end and going to star systems far, far away. We're staying within our own home galaxy today, and we're talking about exoplanets, planets that orbit stars other than our sun. When we research exoplanets, our telescopes are trained strictly on stars in our own galaxy, and finding exoplanets within the Milky Way is one of the most challenging things that we do as an astronomy community. It requires incredible precision and lots of data and good mathematics. And frankly, stars in other galaxies, even Andromeda, are just too far away. Remember that planets, friends, don't give off their own light. Okay? Planets don't give off their own light. So the fact of the matter is, we can detect planets, and there's a number of ways that we do that. When we're talking about detecting planets, one of the primary things we do is we look for the effect of gravitation. It turns out that if you have, and of course I have a model for everything, here's a model of a star and a planet. Let's make our planet smaller because planets are generally much smaller than stars. Let's go ahead and take our small planet here. As the planet orbits, the star does not remain stationary, my friends. No, the star does not remain stationary. And as the planet oscillates from one side of its orbit to the other, it pulls the star back and forth. So as the planet moves this way, the star does too. As the planet comes back on the other side, then the star moves toward the planet. And so as we look at these stars, we see these wobbles. Now, interestingly, no matter how the planet orbits its star, at some point it's pulling that star a little closer to the Earth. At some time, it's pulling the star a little bit away from the Earth. And this back and forth movement causes the frequency of light from the star to change. When the star is moving toward us, even at a few kilometers per second, when the star is moving toward the Earth, then the light from that star is blue shifted. And when the star is tugged by its planet and moves away from the Earth, the light from the star is red shifted. So as this planet, which may be too small for us to see, tugs its star back and forth, then we see, watching the light from the star very carefully, that at first the star's light is red shifted and then blue shifted, and back and forth it goes. Red shift, blue shift, one shift, two shift. No, the red and blue shifts go on, and they have a regular pattern in time. If this was chaotic, if it was a random flickering of red and blue as if the star were vibrating, we would be looking for some other interesting and new phenomena. But the fact of the matter is that the timing of the shifting red and blue moving forward and back is precisely timed with the motion of the planet around its star. For our Earth, we would be tugging the Earth, would be tugging the sun, and we would, if we were observing from a different star system trying to detect the Earth this way, we would expect to see the sun red shifting and blue shifting every 6 months as Earth was on one side of its orbit or the other. Of course, if you have multiple planets, the signal becomes more complex. But we use a mathematical analysis called Fourier fast transform, or FFT, and we can pull out the various signals and separate out the periods, and that's how we figure out multiple planetary systems around different stars. This back and forth motion with redshift, blue shift is called radial velocity detection. Why do we call it that? If you think about a star, if my head represents the Earth, there it is. It's not colored blue, but let's go with that. If my head is the Earth and this is a distant sun moving slowly as its planet orbits and it moves toward me and away from me, if you imagine a system of coordinates centered on me, on the Earth, and radiating outward into space, it's only when that star moves back and forth on a line precisely aligned with the direction to the Earth that we see this red and blue shift happening. That's why it's called a radial velocity detection. The second way we can look at stars and see if they have planets is we can watch for something called a light curve detection. Now, for this to happen, as you can imagine, if I have a star here and the planet crosses in front of that star, the camera is now the Earth. You are the Earth looking, dear observer. And as the planet goes in front, we get a slight dimming of the starlight's intensity. The brightness of the star goes down momentarily. Yes, normally even the biggest planets are no more than about 1/10 the diameter of their star, but you can still see the dimming. You can detect it if you're watching the brightness of the star very carefully. And this happens when we have light curve detection. However, if we think about this, if we have a planet and we have a star, and if that planet is going around this way, well, it would never cross directly in front of our star, so we wouldn't see a detection that way. It's only when the orbit is edge on, so that that planet crosses as we watch it directly in front of the star, that we get that dimming, and this is the light curve detection. The third methodology that we have so far, and there's actually 4, but the third methodology we're going to talk about today is a gravitational microlensing event, which sounds really cool. Some of you may have heard of gravitational lensing. Sometimes it's called Einstein's ring. If you have 2 galaxies, one in the far distant background that is too dim to see, and another galaxy in the foreground, the nearer galaxy's gravitation can cause light to bend around it and refocus, so we can see this odd kind of gravitational lensing. It turns out that if you have a planet pass in front of a distant star, one that's far away, you can get this microlensing, and very temporarily the star will spike in brightness. Now, you might say, well, how far apart do planets and stars have to be for this microlensing to occur? Typically many light years apart. You're like, wow, what's happening? Do you have 2 stars lined up very closely so that is one's planet? No, that's not what's happening at all. It turns out that early solar systems can be rather chaotic places, and what we will sometimes see happen is large planets will be formed farther away and they will migrate inward, and sometimes when they do, they play gravitational crack the whip or gravitational slingshot, and one of the smaller inner planets can be flung completely out of that solar system. It travels and escapes its star's gravitation, and now it's traveling in interstellar space, dark, cold, permanently frozen. These are called rogue planets. And so we have another new class of planet. We have our planets, which we still argue about which ones are and which ones aren't. But we have exoplanets, and now we have rogue planets. Rogue planets were created around a star. They don't orbit any star anymore. They just travel in orbit around the galactic center, just really quite isolated. All of these methods are really cutting edge. We've also been able, in very recent days, to be able to actually directly image planets around other stars. This is perhaps the most challenging sort of events where we focus in very tightly on a star and we use a mask, kind of like a thumb over the lens to block out the light from that star. And then we look in the area surrounding the star and see if we can find a planet. We can do this. We've done it a few dozen times, but typically we're talking some kind of a super Jupiter, something that's between 2 and 25 times the mass of our Jupiter, a really gigantic planet, and something that's quite far away from its home star. But we've imaged a few of these. So let's go back and take a look at the history of all of this. How long has this been going on? People have been trying to do this for more than a century. Matter of fact, the Sproul telescope, which is owned by NWA Space, it's a current ongoing refurbishment project. The Sproul telescope at Strathmore University back east was once used in an early attempt to detect exoplanets. They were not successful because it's a very challenging task. But the first actual exoplanet, you'll be happy to know, was discovered by accident. How many times do we hear this sort of thing? Oh, gee, there was this wonderful project, and we were just trying to clean the pigeon poop out of our horn antenna so we could get a nice clean signal. And what did we discover? The cosmic microwave background of the universe. Well, the first discovery of exoplanets was much like this. So what we're looking at is we're looking at a couple of fellows, and I'm going to try to pronounce a name here, and my sincere apologies. I think it's Alexander Woltson. That's my guess, and I'm sticking to it until I hear from Dr. Woltson himself. His partner was Dale Frail, and they were exploring a pulsar. They were looking at pulsars. The pulsar was PSR B1257 plus 12, which sounds like something out of a science fiction story. Anyway, why couldn't they have just named it Bob? I don't know. But anyway, they were studying this lovely pulsar, and they were expecting a certain frequency. Why? Well, it turns out, what's a pulsar? If you have a normal star, like our sun, say something about 1 million kilometers in diameter, at the end of its lifetime, its nuclear fuel gives out, and it collapses. Gravity wins. Gravity always wins. When the star burns out and the last of its nuclear fuel is expended, it no longer has the energy to keep itself inflated against gravity, and the entire thing collapses. Now, if it's somewhere around 1.4 to 4 solar masses, it collapses to form a neutron star. A neutron star is quite small. Let's take a 1 million kilometer plus diameter star. Let's blow it up into a red giant of about 20 million kilometers diameter, and let's collapse it 1 million times into something that's only 20 kilometers in diameter. So we're taking all the material from the star and we're collapsing it down into something the size of a modest city center, 20 kilometers in diameter. Holy cow. Well, think about the last time you watched the Winter Olympics and you see the lovely skaters spinning, and then they pull their arms in and they spin incredibly fast. This is a form of physics called angular momentum, and when you decrease the radius, you increase the velocity. And so these stars have collapsed on an order of 1 million times, and so they have sped up their rotation rates accordingly. Our sun happens to have about a 26-day rotational period. Well, this pulsar they were looking at, not unusual. They were expecting something about 0.00622 seconds. So about 62 thousandths of a second. incredibly fast. And why the pulse? Well, these neutron stars tend to be highly magnetized. We compress everything, including the magnetic field. And the magnetic field, the poles, the magnetic north and south, are places where a lot of radiation can escape. So we think about these magnetic fields, these very powerful magnetic fields hold charged particles in, but they can escape. So we essentially have a type of lighthouse. Hi, Josh. Josh is logged on, giving me a thumbs up. Thank you, buddy. Appreciate it. And Senthil, welcome back, buddy. Recognize your name. Glad to have you back on How Do You Know? And Mike Wiesner, our old friend and colleague. Thanks, Mike. Appreciate you joining us today. Can habitable planets exist around a binary star? You know what, Connor? We're going to deal with that in just a second here, so stay tuned. What's happening? Magnetic poles don't align with the rotational poles. Just like on Earth, our magnetic north and south are not precisely aligned with our rotational north and south. And so as these poles spin around, it's kind of like a lighthouse. And each time the pole sweeps past us, it's like having a flashlight that points towards you momentarily, big flash, and then it spins away. Well, you're seeing these things spinning so that you're seeing a pulse every 6/1000ths of a second. So essentially, you're talking, if you're seeing both the North Pole flash and the South Pole flash, that means you've got a really fast rotation. About 1/100th of a second or thereabouts. So these pulsars, they're studying these. Dr. Wilson, Dr. Frail, studying these, timing the pulses, because one of the things we hope to be able to see is we hope to be able to watch pulsars and see them slow down, which confirms a lot of relativity and other theories predict how this should happen. And so we're looking for evidence to support our theories here. And what they were finding is that, oh no, there's irregularities in the pulses. They're not happening in the precise time that they're supposed to. And it turns out as they're watching and they're going, oh no, every once in a while, it's like the thing stutters, like it jiggles, like it wobbles, like somebody's putting their finger on the gyroscope. And in fact, we find as we study this, the irregularities are not random. They're not chaotic. They're periodic, which means bump, 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 bump. The irregularities in the pulsar's beat are coming with metronome type precisions. And it's actually Dr. Wilson who solved this puzzle. And he did this fast Fourier transform, and he realized there's two periods going on here, one every 67 days, one every 98 days. And he works out the math and he realizes there's two planets around this pulsar, one of 3 Earth masses, one of 4. Somebody asked us, Connor asked us, can we have habitable planets? The current thinking is these are second generation planets. So you're asked, friends, what's a second generation planet? What's a first generation planet? First generation planets, friends, form around a forming star. We have a protostar with a disk of gaseous and dusty material orbiting around the sun's equator. And as this disk cools, it clumps. Planets form in these disks. We've seen photographs of this with Hubble and Webb, and we see these beautiful disks with gaps where new planets are existing. Well, typically in order to get a neutron star, you have to have a supernova. And it turns out that's not really a survivable event for planets. The planets get, blasted to smithereens. They get obliterated into dust and particles. Whatever was there in terms of planetary crust, atmosphere, cores, boom, it gets blasted into pieces by the supernova event. Not surprising, since supernovae can be lethal from as far as 50 light years away. The radiation burst from a supernova is lethal to everything in quite a distance. Well, so what happens? Turns out the debris tends to form a disk, just like in the protostar. The disk gets clumpy as it cools, and new planets form. So these are new planets formed from the debris of old ones, which Connor, I think, would argue really strongly against a habitable environment. Um, Possible? Maybe. The other problem with a habitable planet around a pulsar is that, of course, all the volatiles, the things like oxygen, nitrogen, argon, carbon dioxide, nitrogen, all these nice lightweight water, methane, these nice ices and gases, boom, they would be blasted out. You would think that what reformed for a second generation planet would be very arid indeed, and probably not very much for plate tectonics, outgassing atmospheres, because, well, that's from radioactivity. And for a star to go supernova to produce a neutron star, it's going to be probably 10 billion years old, give or take, which means much of the radioactive materials in the planetary cores have had time to transition down to non-radioactive states. And so you've got end products of radioactive decay rather than radioactive materials themselves. And so probably these second generation planets are about as dead as it gets. It would be interesting to go see one someday, but that's not anywhere even reasonably within science fiction technology, much less current stuff that's on the shelf. So new planets have been found now by Wolfson and Frail, and they're around a pulsar. Okay, what about, as Connor says, what about habitable worlds? What about planets around sun-like stars? That was the next great quest. And within about 3 years, people found them. And this scientist, Didier Kalos, again, I'm stretching my pronunciation skills here, friends. He was at the University of Geneva. Kalos sounds like it would be an Hispanic name, the University of Geneva. Don't know. Anyway, our friend Dr. Kalos was searching for planets using this radial velocity. He's trying to get as precise a lock on the frequency of a star so we can see very small frequency shifts that indicate redshift, blue shift, redshift, blue shift, so he can detect planets around sun-like stars. Again, an accident. How often does this happen in science? So, Kalos is looking at the star 51 Pegasi. Why? Well, he's looking for a boring star so he can calibrate his telescope. He wants to see how much wiggle does he see in the frequency just looking at a boring old star with no planets. And so he picks 51 Pegasi because it's relatively close to Earth, it's relatively bright, it's relatively isolated in its area in space, so he can lock onto it. And he goes ahead and he looks, and he's seeing, here's a irregularity with a period of just 4 days. It's like, oh my gosh, 4 days? Who ever heard of a planet going around its star in 4 days? The fastest planet in our system, of course, is Mercury, 88 days. You go out as far as Pluto, 248 years. You go out to Quaoar and some of the outer planets, and the periods get even longer than that. But 4 days sounded just fantastic. Well, Kalos tells us that he spent the next, almost all of the next year, convincing his thesis advisor that he wasn't seeing a mistake, that it really was periodic. And indeed, they found this, and the companion had a mass of about 1 Jupiter. So it's a big planet, very, very close. 4 days was lucky because the irregularity was quick. Think about for our planet Jupiter. if you wanted to detect the radial wobble for our planet Jupiter, you would get one blue shift every 6 years, and then 6 years later, a red shift. So the period for a red shift, blue shift would be about 6 years, indicating a 12-year orbit. He was seeing irregularities every 2 days, which indicated a 4-day orbit. Kind of crazy. Later on, this discovery was confirmed by Jeff Marcy and Paul Butler at the University of California, Berkeley, or CAL, as it's known to its denizens. And to date, we've confirmed some 746 planets by radial velocity measurements. So this is quite a good haul. Well, in the early 2000s, we decided to launch a space telescope that would be unlike any we have seen before. This is not like Hubble, where it's in relatively near Earth orbit, where it can move around and point to different things. Instead, we had this idea. Excuse me, we had this idea. Let's take a telescope and put it in a trailing Earth orbit. Let's put it in a 1-year orbit around the sun, trailing behind the Earth by about 1 million miles. Wow, okay. And now let's take and point it at one place in the sky, and it will just stare. So this is unlike every star party experience you've ever been to or had, where somebody says, okay, great, that's Jupiter. What can we see next? No. Kepler was designed to just stare at one place in the sky. And it actually was focusing an area between the constellations Cygnus and Lyra. And it would focus, and the plan was it would monitor 150,000 stars. So it would look at the light curves. It would continuously record the brightness of 150,000 stars simultaneously, which means it's essentially taking video, right? It has a frame rate, so many frames per second, and it's continuing to observe, measure the brightness of all these stars, new frame, measure them all, new frame, on and on and on again. Kepler kind of exceeded its expectations. They were able to observe over 500,000 stars, not just 150,000, but about 500,000. And they were looking for this occultation, where a planet would cross in front of its star, dim the light momentarily, and they were looking for stars whose light curve would regularly drop and then go back to normal. This idea of dimming of a star, if it's periodic, in other words, if it happens on a regular drumbeat-like schedule, that indicates a regular planetary orbit. And we knew we wouldn't see all of them, because if the orbits were not edge on to us, if they were tilted too much, and it wasn't very much at all, then in fact, the star would either be above, the planet would either be above the star, below the star, and so it would never occult the star at all. The star would never be dimmed. So Kepler was only going to be able to see those systems which were exactly precisely edge on to us. And Kepler took a look, and we didn't know what we were going to see. The mission was planned to last about 3.5 years, but you know how NASA and ESA are with their rovers and their probes. I want NASA to build my next car. Because, you know, here's this Mars rover. It'll last 90 days. And 14 years later, it's still roaming around on Mars. So this mission was expected to last 3.5 years. And part of the challenge was keeping it pointed at exactly the same place all the time. To do that, it used 4 gyroscopes, what NASA referred to as reaction wheels. And if you think about a gyroscope, it resists changes in motion. Well, we found that you can actually take a rocket and move the gyroscope and use it to steer the rocket. So we were using 4 reaction wheels, which were supposed to keep Kepler pointed exactly where it was supposed to be. And This was launched in 2008. 4 years later, in 2012, one of the gyroscopic reaction wheels, in fact, did fail. And we're not sure what happened. We just know that it stopped rotating as it was supposed to. And so we're down to these reaction wheels failing. And they basically had a second wheel fail within a year. So this thing is now crippled. But in 2014, the very, very clever people at NASA said, you know what, even with two wheels, we can control it enough to get some good science done. And they decided to have a second chance mission where they would look, and it turned out that they were just going to look at red and dwarf stars this time. And by 2015, Kepler had found over 1,000 confirmed planets in 440 star systems, which means, yes, most of the systems they were finding had multiple planets in them, as our solar system does. Eventually, Kepler completely ran out of fuel. The wheels were not able to be spun at all or moved. And so in 2018, after 10 years on the job in an Earth trailing orbit, Kepler was shut down. And in fact, it had surveyed 530,506 stars. And they discovered and had confirmed 2,662 planets in 9 years. And that was a tremendous amount. Keep in mind that a satellite like Kepler is only going to detect one rather quite massive planets. Kepler's limit of detection was something about the size of Neptune. Oh, and Josh says, will you cover just what a Fourier transformation is? Yes, I can do that for you, Josh. Kepler wasn't seeing the small planets like Earth or Mars or Venus. It was seeing bigger planets like Neptune, Uranus, Jupiter, Saturn. Secondly, Kepler only was in operation for 10 years. It never would have seen a signature for a planet like Saturn, which has a 30-year orbit. And so they were only looking at big, close-in planets. In explaining what a Fourier transform is, let's say you have three people playing the trumpet, and they're all playing different notes, and they're playing a very smooth, consistent note. Well, when these things work together, the notes blend, and you might get a chord, you might get something that sounds quite awful, but in essence, the music that you hear is a combination of all three notes mixed together. The fast Fourier transform allows you to pull out and identify the exact three frequencies of the notes that are contributing to what you're hearing. And so this Fourier transform mathematics, typically done on a computer, can very quickly separate out a signal of these light curves from a star, and they can figure out, oh, how many frequencies do we have? And what frequency are there? So they're able to calculate what the planetary orbits are. And so it's quite exciting. The third search method, or maybe this is our fourth, I guess. Our fourth effort here was the successor to Kepler. This was called TESS. And TESS stood for Transiting Exoplanet Survey Satellite. TESS, like Kepler, could only detect planets whose orbits were edge-on to our solar system. You might say, well, why aren't they detecting them with tilted orbits? You could do that with radial velocity, but that's more difficult than this light curve type measurement. TESS was different than Kepler. It was launched in 2018, and it was designed to be very wide field indeed, with an area 400 times larger than Kepler. It would survey 85% of the sky. So it was one of these all-sky telescopes, and it was placed in a really unique orbit. It was given a 14-day orbit around the Earth, and essentially it went all the way out as far as the moon's orbit and then plunged back in. And you might say, gee, wouldn't that be dangerous? Because if you're flying through the moon's orbit, aren't you sooner or later going to get walloped? Well, in fact, no, because we were using this lovely resonance effect. If you watched last week's program, we talked about orbital resonance. Why doesn't Pluto, since it crosses Neptune's orbit, why hasn't Pluto collided with Neptune? Well, they're on a resonance, so they're never in the same place at the same time. TESS was designed the same way with a 2-to-1 orbital resonance, so whenever TESS reached the moon's orbit, the moon was in fact on the other side of the Earth, so about 500,000 kilometers away. And so the two were never designed to meet. The expectations for TESS were very high. They were expecting 13, maybe 15,000 detections. To date, it hasn't lived up to that. About 6,000 candidates have been detected, but only 268 confirmed planets and 1,720 false positives have been rejected. So TESS has not been really nearly as successful as Kepler. And there's a question, do you need to focus and stare at a small area intensely for a long time? Is that a better measurement? We don't know. It's this science. Remember, we've only been detecting planets around other stars since 1992. So 2022 would have been just the 30th anniversary. We've been sending things to the moon for significantly longer than we've been detecting exoplanets. The direct imaging method, friends, there was an announcement today. I saw it in the Science News, came across my feed today. A new planet was detected and announced today. It was very exciting. These direct image detections are all large, hot, young Jovian planets, planets that are very large, typically 2 to 8 times or more the size of our Jupiter. They're orbiting their stars very close by, or rather, very far away. And so these are far away, hot, young planets. They're quite bright, and we've detected them. The gravitational microlensing, the rogue planets, we've detected 67 of these. And it's kind of interesting. If you take a look and you take a telescope and you say, ooh, I'm going to examine a field of stars for a long time, and I'm going to see if one star goes blip and gets momentarily brighter. Now, by momentarily, we really are talking about a period of seconds where it suddenly flares brighter. Think of that compared to the twinkle that you get from the Earth's atmosphere. How do you sort out those signals? Very challenging science indeed. But in fact, we've detected about 67 rogue planets from microlensing. Also, how rare would this event be? Think of a planet that's at least tens of light years away from a star, and think of how precisely you must line up these two bodies so that the planet crosses in front of the star from your point of view. Realize that a microlensing event that you can observe at one place on the Earth would probably not be visible from someplace else a few hundred kilometers away, because the angle is that narrow, incredibly narrow. And yet we've detected 67 of these microlensed rogue planets. The chance for a confirmation, a second detection, is virtually zero, because that would require the planet to travel tens of light years at least, and then cross in front of another star, lining up precisely with it, us, and the distant star. So these are one-time events, but they've led people to estimate that there may be as many as 1 trillion rogue planets wandering about in interstellar space. Could one drift through your solar system and cause havoc? Anyone seen the classic George Pal film, When Worlds Collide? If you haven't, it's a brilliant science fiction film. Highly recommended. It's in the film library here at the ranch. and it's one of our favorites. Could this happen? Yes. Likely to happen? No. Even scarier, something from the news today. We've detected for the first time not a rogue planet, not a rogue star, but rather a rogue supermassive black hole. You want to talk the doomsday scenario? Let's talk about a multiple galactic merger and 3 or more supermassive black holes play gravitational slingshot game, and one supermassive black hole of 1 billion solar masses gets flung out of the galactic cluster and goes careening through intergalactic space. Once it got out of its galactic cluster, it would be absolutely invisible because there's very little gas in intergalactic space or something like that to feed on. And black holes are only visible when they're feeding, and the infalling gas and material gets heated up and emits radiation. A black hole in intergalactic space would be gone. And we've seen what we believe is strong evidence of a supermassive black hole being ejected from a cluster of galaxies, and it's being whooshed away into intergalactic space. And if that doesn't give you pause, I'm not sure what will. I want to encourage everybody as we're wrapping up today. I'd like you to take a look at the Eratosthenes project that's coming up in a couple of weeks. I'm going to be working with my good friend and colleague, Professor David Sederberg from Purdue University, and we're going to be encouraging astronomers from around the world to go out and measure the solar angle at local noon. And we're going to have a Google form where you can send in your information. We'll do a little bit more on that next week and the week after as we lead up to International Measure the Earth Day, which occurs on March 12th through the 18th. It's actually a week of time because you need a nice sunny day, and not everyone's going to have a sunny day on the one day. We're hoping to get measurements from interested astronomers and citizen scientists from around the world. We'd like to see 1,000 or more measurements if we could get them. And it's going to be quite an interesting experiment, and we're going to do analysis. We should be able to prove 2 things. First of all, we're hoping to get a measure of the Earth's circumference more accurately than Eratosthenes did. Eratosthenes measured the Earth the first time we know of in about 245 BC. So about, 2,500 years ago, give or take. And Eratosthenes came within about 2.5% of the modern measure. We're hoping to do better than that. The other interesting thing is that we're going to be comparing measurements, each observer to all the others. So we're going to be getting hundreds or thousands or tens of thousands of measurement pairs to analyze. And if they're all giving the same circumference within a reasonable error, this is not only going to measure the Earth's circumference, it's going to prove the Earth is a sphere. Because, of course, if the Earth were flat or shaped like a potato, you would not get any sensible measurements, and the agreement at different locations would not align anywhere so nicely. So we're going to be taking a look at that. We'll explain the science of that in future programs coming up. I hope you'll take a look. If you have questions about the Eratosthenes Project and International Measure the Earth Day, please email me at astronomyforeducators@gmail.com. And don't forget, for yourself or the telescope owner in your life, a copy of Star Mentor. Give them the gift of knowledge, the gift of the night sky, the gift of mastery of the small telescope and binocular. That's where we'll wrap up for today, friends. Paul, did we have any fun questions come across the comment stream today?
Just the ones that you already read.
Well, the one that I already read. Okay. Well, that's great. Glad we were able to answer questions today. If you have suggestions for future programs, please don't hesitate to contact us. In any case, I'm Dr. Daniel Barth, and wishing you all clear skies. Good night, everybody.